Okay, in this week we're going to talk about some features that are important for understanding the contrast mechanisms in magnetic resonance imaging. Now, there is an issue here that is we have spent not much time on each of the imaging techniques, X-ray based techniques. And there is something that is different with magnetic resonance, and that is that the interactions between what we can manipulate on the scanner and how the image looks like, these interactions are far more diverse. The mechanisms are far more diverse. And so the point I want to make here is that the contrast strongly depends on experimental parameters. So if we look at an image measured 25 milliseconds after the excitation, this is what it looks like. This is a sagittal cut through the head. We have the nose is roughly here. The back of the head is here, so the head is a bit tilted. This is what the image looks like. If we look at it after 50 milliseconds, we have the appearance of the head like this. After 75 milliseconds and 100 milliseconds. Notice here how the appearance of the head here considerably changes as we increase the time after excitation in intervals of 25 milliseconds. So this is one parameter that we can change. Here's another example of images. As this parameter, time after excitation, is increased, here very short to very long, here we can only see the fluid space, filled spaces in the brain. The next parameters, actually two parameters I want to look at, is the flip angle alpha. We've dealt with that last week, what this is. This is by how much we tilt the magnetization away from Z. So we have taken equilibrium magnetization and we've tilted it away from the Z-axis by this angle alpha, and now it precesses. And the other parameter is the time between excitations, TR. We have on the vertical axis the TR in milliseconds, so this increases from 17 to 1.2 milliseconds to 1.25 seconds, and the flip angle increases from 10 to 90 degrees. What do we notice here? Well, we do notice that the image, as we increase the flip angle here, it becomes progressively darker, and as we increase the TR, the image becomes progressively brighter. There's more intensity. Here it's a very grayish image, here it's essentially a black image. As a side note, the bright dots that we see here, these are actually blood vessels where magnetization is flowing into the image plane, but that's a side note. So here in this matrix, we can see that the flip angle and the time between excitations, TR, this time, these two parameters have an interplay between each other, and they manipulate the contrast also quite substantially. So we're already at three parameters: time after excitation, time between excitations, and the flip angle. These three parameters, they're all under the control of the operator, of the experimenter, that we can change, which can all fundamentally alter the image contrast. So let's recap what we know about magnetic resonance so far. What we have seen is we need a nucleus with non-zero spin, so we have a magnetic moment, and we need an external magnetic field that's generated by our magnet. If we have these two ingredients, we put our subject into the magnet, then we get a nuclear equilibrium magnetization that builds up after a certain time. You can always picture you go into the magnet, and after a while your body builds up this nuclear equilibrium magnetization. Its magnitude is dictated by the Boltzmann distribution. This magnetization, equilibrium magnetization, the thermodynamic nuclear equilibrium magnetization, increases with the number of the spins in the voxel, the magnetic field B0, and the gyromagnetic ratio gamma. So these are three key elements: number of spins in a voxel, gyromagnetic ratio gamma. Those are two parameters that we have limited control over. Gyromagnetic ratio we have no control over. Number of spins in a voxel, we can change the size of the voxel. That can we change. And the magnetic field is something we can experimentally alter. Now if we take all these elements together, then our conclusion is that imaging of the proton, that is the hydrogen nucleus, in water is the most sensitive. Our body is filled with water, so we have a high number of spins. Water is present in concentrations of around 40-50 molar in the body, so it's about 80 molar protons in our body. It has the highest gyromagnetic ratio, so imaging of the proton in water is the most sensitive way to do imaging, and that's for most practical purposes, but not all. We will essentially consider imaging of water in this course. We have seen last week that the thermodynamic equilibrium magnetization m0 is proportional to b0. So if we look at the equation of motion, then the derivative of this equilibrium magnetization with time is equals to m0 cross gamma b0. And frustratingly, this term is 0. So the consequence is that the equilibrium magnetization is along z and it stays along z. Nothing happens. And if nothing happens, we cannot measure anything. So we need to induce some changes. Since all this that we have told you so far, this does not generate a measurable signal. So we need to do something to be able to detect a signal from our nuclear magnetization. So we need to do something to the magnetization to generate a measurable signal, because just leaving our subject in the magnet will not produce something that we can measure. So first, I want to talk about how the MR signal is being detected. What can we detect? And the essential principle that lies behind this is shown here. It is we have a magnetic dipole whose position varies in time, and with a surrounding conducting structure. In that surrounding conducting structure, there is a magnetic field, electric field being induced, a voltage being induced. And all of this is simply Faraday's law of induction. Faraday's law of induction states that we get an induced voltage is given by the time derivative of the magnetic flux. The magnetic flux is given by the surface integral of the magnetic field with the surface vector. So if we look at what this means, we have the surface vector dA here. It's perpendicular to the surface. And what we have in magnetic resonance, the surface is constant. We don't change the orientation, so this is a constant. And so basically, the induced voltage in the coil that we have here is proportional to the change in magnetic field with time. We have Lenz's law to consider that the voltage is induced voltage that produces the current. This produces a magnetic field that opposes the change in magnetic flux. And this all is completely analogous to power generation, whether we do this motion or here in the bicycle power generation for the light of the bicycle. And we'll demonstrate this in the following experiment. We'll take two situations to illustrate the generation of voltage with the change in magnetic flux. So in this coil, I'll turn on the current and we'll see the induced voltage in this coil as we change the magnetic flux. So I'll turn it on. We saw a little blip that's here on this side. And then if I move closer, the movement creates a change in magnetic flux on this coil over here. Likewise, I can take a bar magnet. And if I move that bar magnet here, I'll see already an induced voltage at this distance. If I'm further away, we don't see anything. And it gets really big if we're very close. And of course, if I change the polarity, I'll change the polarity of the induced voltage here. So it goes from both sides as I turn around. We have similarly here with a magnet in here. I can demonstrate this in the following fashion. So if I move the magnet in here, depending on the motion, the direction of the motion, the flux sign will have the LEDs that indicate the flow change. If I'm further out, nothing happens because now we're further away, and with the Biot-Savart law, this induces a lower voltage. So that's a demonstration of the distance effect of the change in magnetic flux on the induced voltage. Okay, now we have to also consider the law of Biot-Savart, which basically says that the magnetic field produced by a current falls off with the distance squared. So it's 1 over r squared. Here's the law of Biot-Savart. So these are the laws of electromagnetism that we're basing our observations on. And so if we take the situation here, we'll take a macroscopic bar magnet. We have a coil that picks up the change in magnetic flux, that converts it to a EMF. And now we will look at what is the induced voltage in this coil. So the induced voltage here is illustrated here with this bar, the magnitude. And now as I rotate this magnet, the voltage changes periodically. Now, if I increase the distance of the magnet from the coil, what happens now? We have still the induced voltage, but due to Biot-Savart's law here, we are getting a reduced induced voltage. And we will illustrate this interaction, the distance dependence, in a small experiment that we have prepared for you. Okay, so what we have here is we have coils. We have the magnet here in blue. The coil, as I turn it sufficiently large, it is moving. The magnetic field, therefore, the flux changes, and that produces the current that lights the light bulb. This is one situation that does not correspond to what we have in magnetic resonance. The situation that we have in magnetic resonance is more like this one. Here we have the magnet in green, and the coils that pick up the change in magnetic flux are around it. And we will see, as I turn this, we will see the induced voltage by the light bulbs up here. So as I turn it, this is like the magnetization in magnetic resonance. We have a change in magnetic field flux. This magnetic field flux is picked up by the coils, and this produces the induced voltage, and here in this case produces light, which of course we can't do with MRI. Okay, so we have seen with a physical bar magnet that when we change its orientation in a conducting structure, we induce a voltage. And as we move this away, we reduce the voltage. Now, the link between a physical bar magnet and the nuclear magnetization is that it is the same effect. It is still Faraday's law. So we have a magnetization. So the role of the rotating bar magnet is taken by the magnetization. We have again our coil here and the induced voltage. As the magnetization rotates, it creates a change in magnetic flux. The magnetic field becomes time dependent here. This term is time dependent, this term is constant. So we have a magnetic flux that changes with time, and this induces a voltage here in the coil. And similarly to the bar magnet, the analogy here holds very well. If the magnetization is further away from our conducting structure, then the induced voltage is substantially reduced. So, if we take this together, then as we increase the dipole distance away from our conducting structure, from this wire, then the induced voltage decreases. So, or in other words, the EMF, the electromotive force, the induced voltage decreases with distance from the rotating magnetization. Now, on a side note, how do we generate the RF field B1 that we have discussed last week at the end of last week? And this works with the following principle. We have a coil here. It's very often the same coil as we have here for detection. We run a current through it, and this current is applied on the coil. Now, this will just generate a linear polarized B1 field, but we can always consider any B1 field that's linear to be a superposition of counter-rotating circular polarized B1 fields, and one of them is going to precess in the right frequency. So if we have this, so we have the current running in the coil, then at this point we will generate a B1 that is indicated here. If we are further away from the coil, remember Biot-Savart, then in this case the current being still the same, but now the B1 field is reduced. So consequence is the B1 field is strongest closest to the coil and decreases with coil distance. So the generation of the RF field is the inverse process of detecting the precession of the magnetization. Here we run a current through the coil. This produces a B1 field that rotates, and this B1 field is the one that we have discussed with at the end of last week. Okay, so much for the theory. What are the consequences now for the fact that as we are further away from the magnetization or further away from our object of interest, either the B1 or the induced voltage decrease. In other words, what does an NMR detector look like? Well, since distance is so important, it implies that we have to optimize the coil geometry, the detector. So ideally, and this is the physicist's view of things, we'd like to put our object into our detector, and this detector should be as tight as possible. Clearly the hippo here is not happy, it's not comfortable. This is not a situation that is ideal for comfort. So what this means also means that our detector is not going to be a detector built for the human body and detect everything from the human body, but it means that we are going to have a detector for every organ of interest. Here's an example of detectors for the brain. They look like bird cages, and indeed they are also called bird cage. Here's to give you an idea how the subject is placed. Here's a mirror for comfort. Here's the subject's head, and here is the structure that detects and excites the magnetization. Here, 3 examples put together. We have the head coil again, we have a breast coil for breast MRI, and for a pelvic phased array, it's a coil that's made for the lower abdomen. Here we have an endorectal coil, it's a small coil, and we have a prostate coil. Now, prostate is an important disease, so we want to be as close as possible with our detecting our signal to the organ. You can imagine, I'll leave that to your imagination to figure out where this coil is placed to be as close as possible to the organ. And here's an example with a rat. So for the rat brain, here's the rat, here's the brain, and here's the detector. That's the coil that was placed on its brain for optimal sensitivity. Clearly, taking such a small subject into the detection of a brain coil or a head coil does not make sense at all, because there the conducting structures are too far away.